Okay. So last time we had, at the end, I was reminding you guys of the following question. If f is differentiable as a mapping from R to R, and say the derivative at 0 is positive, can you deduce that f is increasing in some interval around 0? You all wanted to say yes.
We used A's last time.
We did. And so I reminded you guys of our crazy function. It's slightly modified. So you take our bizarre function that oscillates a lot, but damps down by x squared, and then you add x over 2 to it. So what was the point of this?
Like shifting it. It's almost rotating it pi over 4.
Now it's actually not rotating, because if you rotate the graph of a function, you won't have the graph of a function necessarily.
Right.
But it's pushing it up.
Yeah.
So that basically you're taking the second function here, which looks like this approximately. And it's noteworthy because it's differentiable everywhere. The derivative at 0 is 0. That's clear, right, that it's squeezed between the two parabolas that are tangent at the origin. So if you write down the definition of the derivative, you see the derivative at 0 is 0. But you also see that the derivative varies approximately between -1 and 1 if you do this part, but then adding the x over 2 does what? That's a half. So the blue function has slopes varying between -1 and 1, and then you add a half to it, so it's varying between -1/2 and +3/2, which means that no matter how close you get to the origin, you blow up the picture, you see, yes, it's tilted uphill at the origin, but then you put this wobbly stuff on top of that, and so there are intervals in here, arbitrary close to the origin, where the function is decreasing. And there's a good picture of this in the book. You can actually see, nicely done thanks to a computer. Okay, so what's the moral of the story? The moral of the story is just being differentiable isn't strong enough a condition if you want to have nice behavior. What we would hope is, and what we're trying to do in multivariable today, is have a situation where you have a positive derivative in the real case, say non-zero derivative at a point, and you want to say then nearby the function must be invertible. There must be an inverse function locally. And so what we see is that's false, because for maps from R to R, you need an increasing function or a decreasing function if you're going to be 1-to-1. So clearly we need to add some sort of continuity hypothesis here. So we're now going to consider C1 functions. Because we now believe that without the continuity, that we're up the creek.
Without the continuity of the derivative?
Yes. So note this means f prime exists everywhere, but is not continuous at 0. So I want to now say, okay, as we move on to the multivariable setting, let's put a hypothesis in that the function is C1. So here's what the theorem's going to say, and then we're going to do some examples today. And this is called the inverse function theorem. And if you ask a random graduate student in mathematics anywhere in the country who's studying for qualifying exams in graduate school, this is something everybody needs to know. So get ready. So suppose U is an open subset in Rn, and you have a function, which I'll call little f vector, mapping U to Rn. So what do we notice here, as opposed to other stuff we've done with calculus generally?
We're going from Rn to Rn.
Yeah, same dimension. So the ends match. When we get to the next theorem, not today, but when we get to the next theorem, they won't match. Okay, suppose f is C1. So here you have Rn mapping to Rn, some open set, and there's a point in that open set A. There's a point A in that open set. And suppose the derivative of f at A, so that's a linear map from what to what? So if you think of it as a matrix, it's what sort of matrix? Square matrix. And what's the most natural assumption to make about a square matrix? Yeah, non-singular. So what we're saying here is the best linear approximation of f at A is a non-singular linear map, which means it has an inverse. Then, if the best linear approximation has an inverse, what do you think should be true about the function near A? It should have an inverse. So that's what we're going to say. So we're going to say there's some neighborhood V so that if you map wherever A maps to f of A, I don't remember what notations are in the book, so I'm making up my own notation. As I go here, there's some neighborhood W of f of A, and a function that goes backwards that's going to be an inverse of f, if you think about f just on that little set. So, then there are neighborhoods V and W of A and f of A, respectively, and a C1 function G mapping W back to V, so that's G mapping back, so that G is the inverse of f if you just restrict f to this little set.
Saying G is the inverse of f on V just means if you compose them you get the identity?
In both ways. Yeah,
Right.
so the official way to write it is restrict f to the domain V. That bar means restrict. That now maps V to W, and for that one-to-one onto function, G is the inverse. And there's also still there, huh? Moreover, for any y, which happens to be f of somebody in W, we can give a formula for the derivative of g at y. So for any point in W, it comes from a unique x. And what do you think the derivative of the inverse function should be? It should be the inverse of the derivative. So you take the derivative of f at the point that maps to y, and you take the inverse of that linear map.
Is this supposed to be an integral for the f function?
No, it's just a straight bar.
Okay.
It means restrict the domain to V. I don't think I've used that notation before. So this means instead of having f map all of U, just think of it mapping points in V.
Are V and W open or closed? Or?
They're neighborhoods, so they're open.
Okay.
All right. So this should remind you the last statement should remind you of what formula from last semester? You have two functions that are related. How? How are G and F related?
They're inverses.
They're inverses. So in other words, if I take G of f of x, what does it equal to? X. For all x in V. What should you take and do with that equation?
Oh, you change the derivative.
Right? The derivative of a composition is the composition of the derivatives. Yes, sir?
Sorry, what do you mean for any y equals f of x element of w?
I'm saying for any point in y, any point in w, you can write it as f of somebody in V.
Okay. So that's done too?
Mm-hmm.
Okay.
So what does the chain rule say? The derivative of g composed with f is what?
DGY.
dg at f of x composed with the linear map df at x is the derivative of the function that sends x to x.
Which equals the identity.
That's the identity. So now, this isn't quite enough to say that this is the inverse of this. You can do it the other way, or you can remember, no. What did we prove finally in chapter 4? If you have square matrices,
Determinant 0.
and you have a linear map that works as an inverse on one side,
Which is the inverse of the other.
then it is the inverse. It works on both sides. So we had some theory that we did last semester that said when you know you're working with linear maps from Rn to Rn, you only have to check one side,
What is that after a comma f of x?
respectively. Guess I need to work on my penmanship. Okay, so let's do some examples. So this is one of my favorite examples. Parlor game that magicians or somebody might want to do. I walk up to Cameron and I give him two numbers, positive real numbers, and I say, my numbers are the sum and product of two numbers. And I ask him to give me the original two numbers.
The answer should be 2 and 2.
Well, it depends what numbers I gave him.
Oh.
So, given, let's say, Z and W, positive real numbers, can you find unique real numbers so that Z is their sum and W is their product?
Yes.
So you might even say that it takes a wizard to do this.
Or a math doing monkey.
Or magician.
Can the wizard do it?
Yes,
English language.
Well, you're being a little flip here. So for example, if I gave you 4 and 3,
Are we just asking for a solution to
You
a system
just-
of two equations?
we are. But how do you know there is a unique solution or a solution at all?
Or the 3 would just be 1 and 3, right?
It didn't have to be integers, of course. I mean, do you necessarily believe that there exists a solution and that it would have to be unique?
I don't think there's necessarily a solution.
I think there is.
Um,
I think there's the essence.
No,
of it.
'cause
Let's
try-
well, it
Try
becomes
Z
a
equals-
quadratic if you like.
Oh, it has to be greater than 0.
So I said they were both positive.
Well, try like Z equals 1/10 and W equals 1. Because then if you look at the graphs of those two equations, they never intersect, do they?
Z
Because I'm
equals
thinking-
1/10.
So that would mean x plus y equals 1/10, so you've got a line. And then you've got that, so they never intersect.
Well, so
I don't think there's a number that adds up for the worst case.
Yeah, it doesn't work for the Z's and high W's also.
Z is greater
So
than
if Z
W.
equals 1.
But then it might have two.
Wait, but you didn't specify which one was Z, which one was W, did you?
Yeah.
There's only one number where there's a unique solution, isn't there?
Does Z have to
Z
be
is greater than
Y? W has to be greater
No,
than
there's
Z.
only one
Or Z has to be greater than W, right?
There's only one number
So
where
you tell us which is Z, which is W? Or you
yeah,
Or for
Oh,
I'm
unique,
telling you which one's the sum and which one's the.
it's when x
Oh.
plus
for
y
unique
is
solutions,
tangent to x.
they're like
I was thinking you could choose
So
either
two
one,
curves
or
are
whatever. You give us
it's only
two
when
numbers,
x
then
equals
you
y is there a
Yeah,
unique
so-
solution.
Right,
But
if you can
there's only
switch
one
them around,
number where
you
it's
can be both.
unique.
Well,
You can choose which one is Z, which one is W.
Because like,
So
for
there's-
example, if Z is
Lots of
4,
points where they
W
don't.
is
With the-
3.
oh, if you
There's
think-
lots where they cross two places.
So
But
the
there's
x
one
plus y is shifting up on like
intersection.
x equals y, right?
mhm.
And then x y equals 1 will always kind of be
1.4
on that line as well. So the only time they would ever touch just once is when they'd be
One
tangent, and that would be on
Okay,
x
so
equals y.
so you're addressing the fact
Yeah.
that you think it's highly unlikely that there'd be uniqueness if it exists.
There could be
Because you
some-
could just switch them if they weren't
So
like.
it's whenever Z equals W.
Yeah.
Oh, yeah.
So note that
The
x plus y is y plus x. Deep observation. And xy is yx. So if you have a solution, what can you do? So unless x equals y, if there's one solution, there must be two. So you certainly are unlikely to have a unique one. But now we're wondering about, well, when do we have a solution at all?
Can't there be a unique one if that's the thing, if you take x plus y equals 1, and x, y?
Well, so you're getting the unique solution happens when the x and y are equal, which is exactly, so if you imagine fixing whatever the w value is and moving this till it's just tangent, this should remind you of Lagrange multipliers, then you get a unique solution. And if you push further, you get 2.
Does W have to be greater than, or sorry, does Z have to be greater than or equal to the root of W?
Yeah, would it?
Because that would be like the
would it be
lowest
at z equals
point
W?
of the function.
Okay, so that's all right. So let's investigate this.
Why did you say at least?
Because I haven't proved anything yet, other than the statement that if I have x and y that are different, then the x, y, and yx give me solutions. There might be more, I don't know.
I think it's
Also 1%.
Does anybody else?
Is there a way for the linear line to intersect that in more than 2 places?
like z has to be 2 times.
No.
So basically, it's at those 2.
Well, there's 4. Or no, I.
Those 2 is only those are the intersection.
Okay. All right, so how does this fit in with the theorem? Where is there a mapping F?
From x, y space and w space? X plus y, x, y.
Okay, so I could consider a function that assigns to 2 values x and y, respectively their sum and product. And I could say, well, what can I find out about this function? So F is mapping, in this case, all of R2 as it stands, right? You can do this with all real numbers. Here's real numbers. Is it C1?
Yes.
Sure, polynomials are infinitely differentiable. And so what does the inverse function theorem address? It doesn't address whether you can solve for everybody, but it addresses things locally. So what does the inverse function theorem tell me? Well, let's look at a point. I don't know, x naught, y naught. So what's the derivative at a certain point?
1, or you want to fill out the matrix? 1, 1,
Why not?
Excellent.
Excellent. What's the question you need to ask yourself?
So,
Where's that 0? Or where's that singular?
So, where is this linear map, i.e., for which x naught, y naught is this singular or non-singular?
That would
the
be
determinant,
Is that what theorem have an if and only if?
We show that it's not invertible if the determinant is 0, and so we show that invertible if only if non-singular.
So it's singular if and only if the determinant is 0.
Which is if and only if x
Yeah,
naught
okay.
equals y naught.
Aha. Is that surprising you from what we were discussing? If you're at a point where x naught equals y naught, then do you think this mapping is going to have a local inverse? If you're near a point on where your x and y are the same, then can you uniquely reconstruct, if you have a point in the image, can you uniquely reconstruct the x and the y? So if you were at a point that corresponded to x and y being equal, and you wiggled z and w slightly, so you wiggled yourself to a new hyperbola, and you wiggled yourself, so I should do the colors better here. So you started off at this point with this line, right? So you were saying x and y were equal, they gave me this solution. Now you wiggle the sum slightly, so you take a nearby sum and a nearby product. Isn't necessarily the case that you have a unique x, my picture's completely off here. Isn't necessarily the case that you have a unique x and y.
Yeah, I can agree with it. But you're either gonna get 2 or 1.
Because you can keep moving on the diagonal. And if you're near the diagonal, then near, yeah, my picture's terrible. Near this point on the diagonal, so we had a certain xy and a certain x plus y. Now if you look near this point, and for example, even keep the product the same, you can take nearby sum values, and you'll have two choices that are both, they don't look it on this picture, but they're both very close to this point.
Could you have negative solution to move y the other way?
Correct. Which is even worse. So the fact that this matrix is singular when x and y are equal is not surprising you, because things go kerflooey when you're at a point where x equals y. Okay, so suppose x naught and y naught are different, then this matrix is non-singular. The theorem tells me what? So back here in xy space, you're away from where x equals y. So you're either up here or you're down here. We're now saying that if you have a point x naught, y naught, where x naught and y naught are different, there is a neighborhood where
Is block B different from regular B? Just,
That's the same.
there's only one B, right? That we have to worry about?
none.
Okay. Just make sure we didn't have like a fee scenario.
So this point mapped somewhere. It mapped somewhere to the sum of the product. I'm not sure where that is. Say it's here. What we're saying is there's a neighborhood of this point here and a neighborhood here, so that we have a C1 inverse function going back if you take points in there. So in other words, if you start at a point where you have a solution and you're away from the diagonal, then we're saying wiggling the sum and the product in this neighborhood of the sum and product, we can get back a unique point near the original one.
Could we stretch that neighborhood to like have as an open ball with radius the shortest distance between x, not y naught and y equals x? Open.
So in this case, if I want to talk about u, it could have been all of R2, right? My original domain for f here is all of R2. But having picked a point, I know that I can't go too far without getting into trouble. The theorem doesn't tell me how far I can go. It just says there is a neighborhood. Now what Cameron's saying, in this case, he's pretty sure we don't want to go across here, but in fact that's okay still. The only thing that would get you in trouble, oh no, that wouldn't work. Yeah. So you can't, your neighborhood cannot have 2 points in it that are gotten by reflecting across y equals x. So you can't have any 2 points in your neighborhood that would map to the same point here. Right? If you take an xy here and yx here, those both map somewhere. I don't know where. Both those points would map to the same point there. So your neighborhood cannot contain any 2 points that would map to the same point if you're supposed to have an inverse function. Agreed? So you guys were conjecturing some, what is the image of this map looking like? What are the values for which there exists some point xy that maps to it?
Well, everything except where y is equal to x, right?
No, I'm talking about the image here. So you guys already said that if I drew my sum down here and my product up there, there was no point xy that satisfied that given sum and that given product.
Is it where z is greater than or equal to 2 times the square root of w?
Where'd you get that from?
Yeah, intuition.
So when it's equal, I guess that's where they are equal.
Yeah.
X equals y, and when it's greater, they're not.
Right.
So that's the question I'm asking. If you take ordered pairs and ask, is there some property they must have for this one to be the sum and this one to be the product? What points in the plane do you get? So Jackson, what are you conjecturing?
It's where z is greater than or equal to 2 times the square root of w.
Z is greater than or equal to 2 times the square root of w. And you're not telling me where you got that.
I mean, it's
And if you just look at the graphs and you see like where they intersect, if you do like a couple
the
points.
like the point where xy intersects with x equals y is the square root of w. And the point where it intersects with x plus y is half of z.
Okay.
Are we
So-
requiring a unique x and y
No.
anymore? No.
Well, but that's how I found it though.
Right.
Is with the unique x and y.
Okay. So you're saying if I map
So if z is smaller than the unique x and y, then there are no solutions.
You're saying if I consider the mapping that sends xy to x plus y, xy, and I restrict myself to the diagonal where y equals x, what curve do I get over here?
X and x squared.
So in other words, you're looking at a parabola over here that's given by w equals z over 2 squared. And this is zw. So if I take z over 2, that's x. If I square it, I get w. So in the zw plane, I've got a parabola that looks like w equals z squared over 4. And you're saying, what's the not very prettily drawn parabola. You're saying that this line y equals x back here maps to that parabola.
This is restricted to the positives.
What do you think is true about where all the points other than this line go?
Other than that one.
Are they below or are they above?
Below.
Well, let's see. If we have it to the right.
So there's a very famous inequality. It's below. So for example, I could be where w is 0 by taking one of the numbers to be 0 and the other number to be arbitrary, and that would move me on the z-axis. So that seems to argue that all this stuff maps below and nothing maps above, is what you guys are saying.
Because x, y, positive, if we set z equals to 0, it's always negative.
What if, like, is it,
Yeah, I agree with blue.
if x and y, it seems like if they're really small, then
Yeah.
x plus y will be greater than xy. So is there like a neighborhood around the origin of the graph on the left that maps to, I don't know if that makes any sense.
So here's, what you guys should remember here is that if I take this thing and I square it,
No, it's the same.
remember that? What do you know about the squares of real numbers? Or 0, right? So this is always at least. So it follows immediately just from basic algebra, right? That z squared has to be at least 2w. That's automatic from the algebra. I was hoping Jackson was going to give this to me, but so if z squared is bigger than w, that means you're below the graph of, sorry, z squared is bigger than or equal to 2w means you're below this graph. So what's actually happening when you map the plane over here, what's it actually doing? It's actually folding along this line and folding that line into the parabola.
What do you mean folded?
I mean, it's literally taking pairs of points and folding them to the same point. So it's like taking a handkerchief and folding it along a curve, and the 2 points that correspond to each other when you do the fold gets sent to the same point here. However, what did we conclude? We concluded from the theorem that if you were in a neighborhood of a point away from y equals x, there was a one-to-one onto mapping, and I don't know what the picture looks like, to be honest. It doesn't look like what I drew. But you have a mapping from here to here that has a smooth inverse, a C1 inverse.
Wait, that inverse might not work. Like, going through z that maps to both sides.
Once you pick a neighborhood, then you have an inverse. If you started at that point, you'd have a different inverse that mapped you to a neighborhood of that point. So both these neighborhoods are mapping to this, but you have to choose an initial neighborhood, and then you get an inverse function going back. So this one has 2.
So you can start on the left with two base numbers.
So if you start on the above, where y is bigger than x, and you have a neighborhood that maps 1-to-1 and onto this neighborhood here. If you start below, you have a different neighborhood that maps 1-to-1 onto. Is there a comment?
So you have z squared is greater than 2y. Where does the 4 come from? So we have w equals z squared over 4. Is
Did I
that,
screw up?
well, no, I think It's right, it just is, if we push it all the way to its max.
Wait. Something's wrong, isn't it? Thank you for noticing. Surprised a few more people did notice. Okay, what did I do? These are not the same equation.
No. But I think they're both true. I think if you just like push it to its extreme, you
No.
get.
What did
I think that one.
You got it from when y equals x. You saw for in the right down there at the bottom. You saw for z in terms of x
So
squared.
4 is w equals z squared
W
over 2 squared.
C
It's just
X.
you got the x equals z over 2, and then you just squared x and squared z over 2.
Yeah. Okay,
So
now I'm
there's actually
confused.
stuff above the curve, right?
No, well,
Is you got the z
it's
squared.
because no matter what, it basically is saying that it's greater than 2xy, but x squared and y squared are gonna have value unless they're all 0. And so then it's that I think would make up the
All right.
difference.
That's absolutely
Is there
right.
lunch in?
You
Yeah.
You just know
This is not the best.
It's true, but it's not very strong.
Yeah, that's right.
Yeah, you're drawing like a different graph.
It's greater than equal to 2w plus x squared plus y squared.
X minus y squared.
Right. Yeah, so this is true, but it didn't give me what I wanted. So what should I do?
X minus y squared.
Now what? Yeah, I mean, so this says, well,
Is greater than 2xy.
I see. Right. Of course, everything's stupid. Okay, so that gives you this.
Then it's always larger than 4.
So x squared plus, right.
Let's see.
Yeah, so that gives us the right parabola. Phew, that was bad. Thank you. Thanks, Yiming. All right. Wasn't quite intending to spend that much time on that example. So here's a really important example that shows up all over mathematics. So I'm actually going to switch letters for, I'm going to use U and V just because I feel like it. So here's a function that sends R2 to R2 again. Is it C1?
Yeah.
Yes, it's different.
That's not what I asked. Is it continuously differentiable?
Yeah.
Yeah.
Take partials of these things, they're built out of exponentials and sines and cosines, which are infinitely differentiable. So this is in fact infinitely differentiable. Okay. Tell me what the derivative is.
E to the u cosine v.
Negative u sine. U sine v. U cos.
So what's true about singular, non-singular for this?
When it's always
The determinant of the derivative.
e to u.
Be careful.
e to u times
No.
Cosine squared.
Yeah, cosine squared.
Agreed? What do you know about e to the 2u?
Never zero.
It's always
It's always positive. Would you care to make a conjecture if the derivative is always non-singular? Do you have any conjecture you'd like to make?
You always find a
There's a global antiderivative.
You don't mean antiderivative.
Global inverse.
Fell right in the trap.
But like, it's just periodic.
Yes, Gabe's noticing cosine and sine. What does this function do?
Just like.
We've actually drawn pictures similar to this before. If you fix u and vary v, what happens to this with this function? Fix u, so e to the u is fixed, and then you just go whirling around a circle with radius e to the u. What happens as v goes in multiples of 2 pi?
Same value.
Keeps hitting the same point, right?
It's not like one.
Definitely not 1-to-1. What happens if you fix v and vary u?
Shows something on an array.
Right. Goes an array like that. So this reminds you of what?
Polar.
Polar, but I put an exponential in there.
Which
So-
is like a scalar,
Hmm?
which would be like pretty much a scalar to a polar point.
Well,
I don't understand your question.
What does throwing in the e to the u do?
It means I move, the radius goes exponentially with u rather than,
Like,
also when we did polar, you could only define it when radius was positive. Now I can do u all real numbers. So this is very interesting. So we're saying the derivative is non-singular everywhere, so we have local inverses. We have local C1 inverses near every point. But no global. In fact, each value other than 0 is taken into the offering. Now, what I don't have time left to do is you can actually, in this case, you can actually write down an inverse function locally, as you could have in this case too, by the way. The theorem is used when you can't locally do the algebra and find local inverses. It's of interest when you can't do it, even though the theorem says a solution exists. But what I wanted to point out here is that that you could still do this inverse. Even if you didn't write down a formula for it, you would know what the derivative was because of that formula. All right, so you could write down the derivative of this function. You could say, I know what an inverse matrix for this is, and that's what the derivative of the inverse function would be at the point g of f of u v. Okay, so tomorrow we'll go on with a little bit more discussion of applications of this theorem, and then we'll actually talk about the implicit function theorem. Proofs to follow later in the week.
so you would know the derivative of the inverse function, but would you know the inverse function?
No. I mean, in this case, you can write down the inverse explicitly. You pick a point here, and say, I want to stay at this point, then I can give you a formula. I mean, basically, you have to use arctan.
Okay.
So is it usually when we like e to the u or like sine, because then we were gonna have these different between some point.
Right.